Welcome to Sigma Solver, guys. Before I start the video, I want you guys to smash the like button. This helps the YouTube algorithm and keeps me motivated. And if you are new here, then subscribe to my channel and press the bell icon so that you never miss an update. So without any further ado, let's get started. Today we are going to look at another topic which is related to multi-class classification. So let's read the question first. Consider the outputs and targets for a multi-class classification problem in the table on the right. Use Softmax to normalize the scores into probabilities. Calculate the cross entropy loss and mean squared error loss. Which of the two loss functions should be considered better and why? So we have been given a table to the right which contains 4 classes and their target class A, D and B along with the scores for each class. Once we go through this problem, we will understand that it's quite an extension of the binary classification problems in machine learning. So if you guys want to know what is binary classification, I'll put a few of the related videos in the I button here. You can check them out as well. So moving back to the topic, multi-class classification. Multi-class classification is a section of ML problems where goal is to assign an input into one of 3 or more distinct categories. So just like we had in binary classification, the number of classes may increase here and it is important to have them all distinct from each other. So in basic terms, multi-class classification measures the likelihood towards a single class out of all, right? If we try to understand it in a better way, we are kind of doing binary classification but for all the classes towards this single class against all the other classes in the data space. So in multi-class classification, we need to keep track of 2 things. The raw outputs that are given in the table are called logits and these are converted into probabilities using Softmax, which we will see how below. So first is probability conversion. So as per the given table, what we need to do is basically make it e raised to power I divided by summation e raised to power j. Now if we try to understand this, then row 1 in the given question, so the first row is 1, 6, minus 1 and 3. A will not be considered because it is a target class label for this one. So since this is a numerical operation, we try to make this one as e raised to power 1 divided by the sum of all, right? We just make it in exponential form and try to do the probability for each class based on the others. So this is for probability of class A, probability of class B, C and D, right? Which we will calculate and find these all. These are the calculated values. Next, we do this similar operation for the row 2. So then again, the formula will remain the same, e raised to power that particular number which is associated with the column's score and which is divided by the rows total, right? So this is the idea. Similarly, we will get a numerical values for this row as well, and so on is what we do for row 3 also. So it might be a calculation intensive task, but we need to convert the given logits into Softmax probabilities using this way. Once we are able to do this, then what we do is basically calculate the cross entropy loss. So for that, all the given classes are now one hot encoded. When we say one hot encoded, it means if 5 classes are there, then each one will be identifiable next to one another, right? So this one maybe one of the digits is 1, this one the other digit is 1, like this. We'll see this in action down below. So the formula for this one is loss of cross entropy equals negation of whole summation over I yi times log of pi. Now pi comes from the probabilities that we have calculated in the previous step and yi is the logit. Since this is going to be an iterative step, for each row we will have to compute the loss for the target class. So if we take the example of row 1, if we check back on the question, we see that the target class was A, right? So all other classes apart from A will become 0. Why? Because we are taking one hot encoded data. So if we take row 1 where the target class is A, then cross entropy loss will be minus 1 times log of PA minus of 0 times log of PB minus of 0 times log PC and minus 0 times log of PD, because we are going to consider the target class A, so only that will have 1 as the coefficient, so which we calculate as 5.05. Next we do that for the second row. Here the target class was D, so the cross entropy loss will be similarly found where all the coefficients are 0 except for the coefficient of D. So we calculate that minus of log 0.237, which comes out to be 1.44. Next, for row 3 again the target class will be B as given in question, and then only that coefficient will be 1, right? Similarly, we will find that out. It comes out to be 0.41. Now this was cross entropy loss, which was one part of the given question. Next we calculate the mean squared error loss. So here we will try to again use one hot encoding for the target. This is essential since we are in a multi-class classification problem. So the loss function in here will be determined by a separate formula, which is 1 by n summation over I pi minus yi whole squared inside of summation. So if we try to see it in action, row 1. So in row 1 we get one hot encoding for class A, right? So in only that one will reside next to PA, which is PA minus yi. This time it will be 1 whole squared plus PB minus 0, because this is not the target class, whole squared. Next PC minus 0 plus PD minus 0 whole squared. So which will be calculated in numerical format, and then if we do all the calculation here, then we get 0.47, right? So we understood that if we are using one hot encoding, then only that class will sustain in the logit and rest all will become 0. Next we do this same for the row 2. Now this time the target class is D, so D will have PD minus 1, rest all it will be 0. Similarly, we do the mathematical calculation here and we get 0.251 as the mean squared error loss for target class D. Next we do the same thing again with B. This time it will be PB minus 1. Now what is more crucial in all these calculations is the value of PA, PB, PC and PD is going to change for each row. So if we go above, we will find that we have made the Softmax calculations for each row separately, right? So the place where there can be errors is the value of PA, PB, PC and PD when we put it in the mean squared error loss function. So just make sure that when you are calculating for target class A, you are taking row 1, taking the value of PA from row 1 only. So that being said, now we are in a good place to compare all these three, because we have calculated the mean squared error loss for all the three target classes. Next we compare both of them. So this is the straight numerical comparison for cross entropy loss and mean squared error loss for each of the classes. So A has 5.05 and 0.47. So this is the loss for each of the classes. Now a common observation here at this problem is cross entropy is seen almost greater than or equal to the mean squared error loss. It's not always the same, but generally this is seen. So why it is so, we can understand by the following properties as described below. Cross entropy loss is primarily designed for classification problems that have probabilistic outputs, right? Not those which have, you can say, discrete outputs or a split decision problems, not like that, but very probabilistic classes are there. So if one not, then other with probability 1 minus p, like this. Next, the main root cause for penalizing such harshly to get such large loss values is that cross entropy loss kind of penalizes misclassification very heavily, and that too if the model is kind of more towards strict on incorrect predictions. What do I mean by that? If a particular classification is made wrong, then the model kind of reverts its weights very drastically towards the other side, right? So if let's say W1 alpha 1 plus W2 alpha 2, then due to W1, if the model took a wrong decision, then it will greatly reduce this weight in the opposite direction and increase the other weight, which is W2, right? Then what we see is for mean squared error loss, this does not directly optimize the probabilistic classification. So this is more towards the problems that are solvable using regression. So there what do we have is basically the Euclidean distance parameters reside, right? So those problems where Euclidean distance parameter plays a crucial role, there mean squared error loss is quite usable and is used in the ML algorithms. MSE also penalizes small errors evenly. So if a particular classification line has been made in the space, then the deviations are basically penalized equally, so that the line kind of stays the same but rearranges itself in a way that does not differentiate drastically from the original line, right? So the idea is to do it in a gradual way using maybe gradient descent and all, and then get the line to a place where the errors from the extremes is minimized. So it penalizes small errors very evenly, and it does not differentiate between correct and incorrect classes. So the conclusion that we get out of this is cross entropy is generally better for multi-class classifications task because it directly optimizes for probabilities and penalizes misclassifications very appropriately. On the other hand, mean squared error loss may not be as effective because it treats probabilities more like regression outputs rather than class probabilities. So that's been it. If you still have any doubts, then feel free to reach out in the comment section below. If you liked this video, then give it a thumbs up and subscribe to my channel for the upcoming videos. Till then, happy solving.
Hey there, before you go, I've got some fantastic content lined up for you. Over here, we've got some videos and playlists you might enjoy. But first, if you haven't already, make sure to hit that subscribe button and ring the notification bell so that you never miss out on any of our future uploads. Thanks for watching, and I'll catch you in the next video.